This is lesson 2 from Unit 5 on Extrema on an interval. We're going to be using calculus to find extrema on an interval, meaning we're going to find the max or the min. It might be over the function's entire domain, or it might be on a closed interval. So this is how we do it. We've got the definition of absolute or global extrema. If f is a function on an interval I, then y equals f of c is the absolute maximum on I if and only if all of the f of c is bigger than all of the other y values, right? All of the other f of x's in that interval. And it's a global or absolute minimum on I if that value, that y value at c, is less than or equal to all of the other y values on the interval. So for example number 1, it gives us a graph of a piecewise function, and it's called h of x. Determine the extrema of h of x on the interval from a to f. So what you want to be looking at here is, you'd be following like your a value over. This would be your h of a here because I followed it over from that point. This one right here would be your h of b. Follow this h of c over. It looks like h of c and h of a are the same about. And follow this point over here, and this looks like h of d. Follow this one over, and it looks like h of f is about right there. Follow this one over at E, and you've got h of E up here. So we can see that the highest y value is your h of E. So from here, our h of E is the absolute maximum on that interval, on the interval AF. And that h of d is the absolute minimum on AF. And so what about all the other ones? Well, you've got relative extrema, so that if I looked in the neighborhood of something, so I'm just going to erase these right now so that we can kind of look in the neighborhood. And I know I've done this with you in class. And so if you are looking in the neighborhood of B and just focusing on only this right here, just looking at those points, you can see that in the neighborhood B is a minimum, or h of B, I should say, is a minimum. So we could say that our h of B is a relative minimum. On that closed interval, it had absolute maximum and absolute min, but this one, it would be considered in the neighborhood a minimum. And then if we look at the next one, if we look in the neighborhood of C, and so we're just focusing here, h of c is going to be a relative maximum. And we already said that D was our absolute, okay? And we said that E was our absolute. So we're not going to look at our endpoints here. The only time we consider our endpoints is if one of our endpoints is an absolute. Because look at this definition that we have coming up here. It says relative or local extrema, y values on the graph of a function where the function changes from increasing to decreasing and vice versa. And so some books say that you can have this be endpoints. We're going to go ahead and say that it can't. It can't be endpoints. That the only time it's going to be endpoints, that the endpoints would be something that we would discuss is if they were the absolute or the global extrema. So we didn't even worry about A and F here because they ended up not being. Some books look at it as, you know, in the neighborhood. There, you can't really do a neighborhood. You can only do a right-hand neighborhood for A, and you can only do a left-hand neighborhood for F. But if it was a book that considered that, this would be, your H of A would be considered a maximum, a relative maximum in the neighborhood, but only coming in from the right. And H of F would be considered a relative minimum, but again, only coming in from the left. So we just, you know, there's two different thoughts, and different books have different ways to write about it. And we're going to talk about it as just looking at the interior on a closed interval. Now, if it's the domain, the same holds true but you would have, like on the domain of f of x equals that the square root of x, we have this function, and we do consider that this endpoint is the absolute minimum. So, you know, there's different things that go on, but if you're on a closed interval like this, not talking about the domain of the function, that we typically don't consider these endpoints, and this would be considered an endpoint anyway because it is the absolute minimum. So that's why this one is considered that. So when you look at it like that, your value, your 0 at 0, so your y value is 0 at x equals 0 is considered your absolute minimum for that function. So since it is an absolute, that makes sense. Okay, so now, definition of relative / local extrema. If there's an open interval containing C on which f of C is a maximum, then f of C is called a relative maximum. And if there is an open interval containing C on which f of x is a minimum, then f of C is called a relative minimum. Again, those endpoints do not have an open interval. It's only coming in from one side. Okay? And then there's some noteworthy thoughts that they put in before we do example number 2. When we say an open interval containing C, we mean that we can find some interval AB, not including the endpoints, such that C is between A and B. That is, C will be contained somewhere inside the interval and will not be either of the endpoints. A relative extrema is slightly different than an absolute extrema. All that's necessary for a point to be a relative maximum is that for that point to be a maximum or minimum in some interval of x's around x equals c. There can be smaller or larger values of the function at some other location, but relative to x equals c, f of c is smaller or larger than all of the other function values in the neighborhood of c. And that's what we were talking about up here when I was talking about in the neighborhood, because obviously your h of c here was not, you know, the highest point. Okay, we had other higher points over here, but since it was in the neighborhood the highest point, it's called a relative maximum. Okay, so now example number 2. We've got, consider the graph of y equals g of x shown at the right. State the relative extrema of g of x. And so for this one, you can clearly see that you've got an absolute, and sorry, but I guess they wanted absolute for B and they want relative for A. So I right away can see that my absolute minimum, oh gosh, sorry, that does not even look like minimum. Let me erase that. I don't know, I'm writing funny here. Absolute minimum of -8 occurs at x equals -3. Okay, now I see these arrows going up, meaning that there is no absolute maximum. because it just continues to infinity. Okay, so that means that that g of x is unbounded above, right? So there is no absolute maximum. Now, relative. So you can see where right here in the neighborhood, that's the highest point. So I have a relative maximum of 2. Relative maximum of 2 at x equals 2. And then on this one right here, I can see that that's the lowest in the neighborhood. So I have a relative minimum of 0 at x equals 4. Okay, so those were 2 places where we had relative maximum here in this neighborhood, and we had relative minimum here in this neighborhood. And the other one was absolute. All right, so example number 3. Consider the graph of y equals f of x on the closed interval from 0 to 12. Shown below. Part A, find the relative extrema of f of x. Okay, so to me, absolute is easier to find first. But, you know, that's just me, so I probably would do this absolute because I can see that -2 is my absolute minimum. So I would say, okay, I've got an absolute minimum of -2 at x equals 2. And then I can say that I have an absolute maximum of 7 at x equals 7. Absolute maximum of 7 at x equals 7. Now, remember what I've told you before. It can be relative and absolute at the same time. We're looking at them differently right now, but every absolute is also a relative because it's also in the neighborhood, the lowest point. So for instance, this point right here at 2, -2, we said it was the absolute minimum, but it's also in the neighborhood, the lowest point. So it can be considered relative, but we're going to just be more specific, and you know, it's absolute. It's also relative. It's like a square and a rectangle. Okay, a square is a rectangle, but it's a specific type of rectangle. So find the relative extrema. Now, if we go to relative now, we have a relative maximum and here's where we're going to say that it's also relative, a relative maximum of 7 at x equals 7. We've got a relative minimum of 2 at x equals 10, because here's the minimum value here in the neighborhood. And we have a relative minimum of -2 at x equals 2. So this is where we want you to look at. So, you know, for the one above, could we have said that in the neighborhood, for this example number 2, could we have said that in the neighborhood that this was a relative minimum? Absolutely. Okay. You could have also included that in your, you know, because it's also a relative minimum, but more specifically, it's an absolute. Okay. So here we decided to go ahead and include them just to show you that, hey, you can include them it's relative and it's absolute sometimes. Sometimes it's just relative. Okay. All right. So now that leads us to what conditions would be necessary in order to have both an absolute maximum and an absolute minimum. So the extreme value theorem. If f is continuous on a closed interval ab, then f has both a maximum value and a minimum value on that closed interval. So what they're saying is, as long as you're looking at a function on a closed interval, it's from a dot to a dot. That means that you are guaranteed to have a maximum and a minimum on that interval as long as it's continuous on that interval. So it might be at the endpoints, but it's guaranteed to happen. So for instance, if I said, f of x equals x squared, and I only looked at it on the domain from negative infinity to positive infinity, then it's not guaranteed to have a max and a min, because we know what that function looks like, and it only has a min, okay? It's unbounded above, so it doesn't have a maximum. And so it's not on a closed interval, so that makes sense. So now, what if I said, let's look at the same function, only this time I want to look at it from, let's say, 0 to infinity, okay? And so we're only looking at half of it. So it's closed on one side, but not on the other. Well, that means it's going to have an absolute minimum, but it's not going to have an absolute maximum, because this is not a closed interval. It's a half-closed interval. So this does have an absolute min of 0 at x equals 0, but it doesn't have an absolute max. So no absolute max. This one only had an absolute min of 0 at x equals 0. Sorry, this pin's not, this is supposed to say of 0 at x equals 0, okay, absolute min. But if we take f of x equals x squared and we look at it on a closed interval, let's say from -1 to 3 or something like that, that is a function on a closed interval. The extreme value theorem guarantees that it will have an absolute max and an absolute min. So we're only talking about it's continuous on a closed interval here. And you can see that your absolute min is 0 at x equals 0. So it's on the inside of the function. Your absolute max is 9 at x equals 3. And so the absolute max occurs at an endpoint, okay? So that's extreme value theorem guaranteeing that if you have a continuous function on a closed interval, that you will have an absolute max and an absolute min, guaranteed. So, example number 4. For each graph below, explicitly state where the hypothesis of the extreme value theorem fails on the interval 0, 3. Then determine if the function has an extrema on the interval. Okay, so let's look at these functions. So this one, for part A, the extreme value theorem does not apply. Because f is not continuous. On 0, 3. Okay, that's why the extreme value theorem does not apply. Does it have an absolute max and an absolute min? Well, the absolute max is 4 at x equals 1. The absolute min is 1/2 at x equals 0. Okay, so what about B? Okay, extreme value theorem fails because f is not continuous on 0, 3. Absolute max is about 4.5 at x equals 0, and there is no absolute min because there's an open circle there. That means that there is not an absolute min. It'll be approaching 1, but it never actually equals 1. Y value of 1. Okay, and then for C, extreme value theorem does not apply because f is not continuous on a closed interval. So the whole thing is it has to be on a closed interval. And you can see there that they're showing us the function on the open interval at 0 to 3 without having actual points there, okay? It should have been on a closed interval, 0, 3, like that. But it was, an open interval like that. That's what it's showing it to us on. And so, therefore, there's no extrema. No extrema for C. Okay, for part D. If you notice, your endpoints are open circles. So again, even though it's continuous in between those, since your interval is an open interval, 0, 3, that's why your EVT does not apply. So extreme value theorem does not apply because F is not continuous on a closed interval. So I'm going to underline the word closed interval, 0, 3. Okay. And for this one, though, I'm going to have to erase some of this old stuff so that I can write a little bit more about that letter D, because I forgot to include our, it does have an absolute max of about 4 at x equals about 1.2. I can say approximately, and I can put a little approximately there, and an absolute min of about -3/4 at x equals 2. That does look like 2, pretty good, but it's about -3/4, or maybe you could say -1. Okay, that's fine. You're doing approximation, so you can't, it's not like you can be wrong. So the extreme value theorem gives us the knowledge of when extrema occur, but how will we find them algebraically, or how will we find them algebraically when given an equation only, without the benefit of a graph? So our next question should be, how can we identify all the values of x where extreme values occur? And that's when we will start looking at what we know about functions that we learned in pre-calc, and also using our derivative and how that derivative is going to help us. So for each function shown below, justify why the extreme value theorem can be applied or why it does not apply on the given interval. So if I look at this f of x, right away I think that there is a vertical asymptote at x equals 2, and that is a discontinuity, okay? That is a discontinuity. And I think, well, if my closed interval has 2 in it, then I know I can't use the extreme value theorem. So my closed interval is -4 to 4, so that does 2, lies in between those two values. So the EVT does not apply for f of x on -4, 4, because f is not continuous on negative 4, 4. There is an infinite discontinuity at x equals 2. So if I would have given you this same function on the interval from, let's say, negative 4 to 0, you could have applied the extreme value theorem, okay? So, because that did not involve x equals 2. So you just have to be careful, and look at, okay, think about your function and what it has, and then think about your interval and whether there's a problem in that interval. Okay, letter B. We've got e to the x minus 2 plus 1 is our function from negative 5 to 5, and I don't think there's any discontinuities on an e function that has been shifted or anything. So g of x is continuous for all reals. So the extreme value theorem applies for g of x on negative 5, 5. Okay? And then part C, we've got to think about what the domain of this function is. I know that your x plus 2 has to be greater than or equal to 0, so x has to be greater than or equal to negative 2. So that means your domain is from negative 2 to infinity. So we do have to keep that in mind, and when we look at the interval, it's going outside of your domain. So therefore, your function is not continuous. So we say that since h of x is continuous only for values x greater than or equal to negative 2, the extreme value theorem does not apply for h of x on the interval from negative 6 to 6. Okay? And so now we have the definition of a critical number. A critical number value of a function f is an x value, x equals c, in the domain of f such that either f prime of c equals 0 or f prime of c does not exist. Notice they're talking about f prime, so we're using the derivative here, and we're looking for where it's 0, what makes it 0, what makes it not exist. And so if x equals c is a critical value, then c comma f of c is called a critical point. And so, theorem, relative local extrema can only occur at a critical value on an open interval. So, absolute extrema must occur at a critical number or at an endpoint of an interval. And then that leads us into using the candidates test to determine absolute global extrema. So now we need to put these ideas together with a little direct practice. And we're going to develop an algebraic approach to what is called the candidates test for finding extrema. All right, so now we've got example number 6, and we are asked to find the local extrema of the function on the given interval, provided that the extreme value theorem is applicable. If it is not, justify why. So we've got a polynomial function which is continuous from negative infinity to positive infinity, so therefore it would be continuous from negative 1 to 2. And so we can apply the extreme value theorem. So what we're going to do, is we're going to first take our derivative. And so our derivative here is going to be 24x squared minus 6x minus 9. And then we want to think about how can we set this equal to 0 and find what makes it 0? Because I know there's nothing that makes it not exist, so, but we're looking for, remember up here, we're looking for where the derivative is 0 or does not exist. Okay, so we're going to focus on where it's 0. I notice that I can factor a 3 out, and I'm left with 8x squared minus 2x minus 3 I would then try to factor this. And I'm going to try using 4x and 2x. And then I think about that this has to be 1 and 3. So I'm thinking about where should I put my 3, where should I put my 1. If I do this, I've got a 6 and a 4. And if my 6 was negative and my 4 was positive, that would give me that negative 2x in the middle. So this is my factored form. And so using my zero product property, I get that x is equal to 3/4 would make it 0, and x equals negative 1/2 would make it 0. So these are called my critical points. And so now I'm going to do something called the candidates test. And when we do the candidates test, I don't know if I can fit it in here because I'm writing so small, but you basically just make a little box and you're going to look at x and f of x for certain values, okay? You're going to look at them at your endpoint, and notice your endpoints are negative 1 and 2. So I know I'm going to look at negative 1 and see what my y value is. The next thing I see that comes up is negative 1/2, which is one of my critical points. Then 3/4 is one of my critical points. And then I would do my last point of my end of my interval, 2. So you're basically using your endpoints of your closed interval and your critical points. Now, sometimes you might have a critical point that's not in that interval, and then, you don't have to worry about it because you're only focusing on what's in this interval from negative 1 to 2, okay? So if we put negative 1, and we can put this in our calculator now, you can put f of x equals 8x cubed minus 3x squared minus 9x plus 2 in your calculator. And you can, pause the video, get that in your calculator so you can see what these values are, and then just use your table to find your values. You will see that at negative 1, you get 0. At negative 1/2, 4.75. I included 0 here, but I don't know why. At 3/4, negative 3.063, and then at 2, I got 3.6. So we did not have to include 0 because that was not one of our critical points, so I don't know why I did that in my notes. Anyway, sorry about that. You can see, now you're just going to focus on these y values. Your smallest y value occurs at x equals 3/4. So that is your absolute minimum. So you have an absolute minimum of negative 3.063 at x equals 3/4. And you have an absolute maximum. If you look along these y values, your maximum is going to be a 4. Oh, hold on. I'm reading my notes wrong. This was actually, I thought it was 3.6. Now that I draw it closer, 36. That's going to make a difference. So an absolute maximum of 36 at x equals 2. So your minimum, for your candidates test, again, you're taking your endpoints and your critical points. So our